Begin me. Hi all, welcome to today's seminar, which is organized by the EuroCC2 project. The EuroCC2 is a pan-European project with more than 30 countries participating. The goal of EuroCC2 is to enhance Europe's competencies in advanced technologies such as high-performance computing, machine learning and artificial intelligence, and high-performance data analytics. Today's seminar is entitled Aurora, a foundation model of the atmosphere, and is presented by Professor Paris Perdicaris. Paris Perdicaris is an associate professor of mechanical engineering and applied mechanics at the University of Pennsylvania, and a principal researcher manager at Microsoft Research AI for Science. His research interests span a range of topics at the interface of computational science and deep learning, including the development of foundation models for weather and climate modeling, physics-informed neural networks and neural operators, generative models, and uncertainty quantification for sequential decision-making in scientific and engineering applications. Let's now welcome Professor Perdicaris to the floor.
Thank you. Thank you very much for the invitation and the nice introductions. Are we already sharing screen? I'll just go, or we have to do that.
Got it. How can I? He told me to share this screen.
Oh, this screen,
yeah. And then full screen?
Yeah.
He told me the opposite.
All right. Hopefully this works. Or we need to join the audio as well. I'm not sure. Well, for whoever is attending online, let us know if something is not working. All right, so welcome. Thank you for joining. So today I'd like to present some recent work that I completed with a team of researchers at Microsoft Research AI for Science. Most of us are based in Amsterdam, but it's a global program. We have some team members in the UK, some of them are in the US. And the goal of this work, the overarching goal, is to really try to explore the most recent advances in deep learning for enabling scientific discovery across different problems and different scales. And when we all started, we were really looking for problem settings that were sort of ready to be disrupted by deep learning. And those problem settings typically involve problems that involve high impact applications, but also involve high quality data that is ready to be processed by those systems. So my background is mostly in computational science and fluid dynamics, and I think one of those problem settings that we identified back then was the setting of weather forecasting, because the way that the Earth system has been monitored over the last 5-6 decades has been quite unique. We have access to really, really vast quantities of data. Let it be the output of physics-based simulation models, let it be observational data from satellites and weather stations. And we think this is a really interesting setting for developing deep learning methods and try to disrupt this field. So the focus of this talk today will be on Aurora, which is a first version of a large scale of what we call foundation model of the atmosphere. And for those of you that are not familiar with foundation models, I'll try to take one slide to kind of motivate the topic. So let's see. Okay. All right, so deep learning foundation models. So this is just a terminology. Basically, a foundation model is just a large-scale neural network whose goal is to be trained in two distinct different phases. So the first phase is typically called the pre-training phase. And in this phase, the goal of the network is not to become accurate in solving a specific prediction task. Instead, its goal is to try to learn and extract general purpose representations from a very large corpus of diverse training data. And typically, this is the most computationally demanding and expensive phase. We'll get back to the details of that in a little bit. But then once a model has been pre-trained, then it will leverage this concept of transfer learning to be fine-tuned in a second training phase in order to become accurate at solving specific prediction tasks of interest. So for now, just keep in mind that foundation model is just a very large neural network, and we train it on two different phases. Phase one helps it extract representations from large volumes of data. Phase two leverages those representations and fine-tunes them to adapt for solving specific prediction tasks. And this paradigm of foundation model has really introduced a paradigm shift in recent years in machine learning. And this new paradigm is sort of eclipsing the use of specialized models we used to use in the past, where you might have a single data set, you train a single model focused on one task, and then you're happy with that. Most of the current literature in ML involves in one shape or form this concept of transfer learning and foundation models to build more general purpose models that can generalize across different prediction tasks. And foundation models have already revolutionized or are in the process of revolutionizing different scientific fields. So very recently, there was a new Nature paper from Google DeepMind on AlphaFold 3. So that's an example of a foundation model that can reason over protein structures and sequence data. Of course, you all know GPT-4 as an example of a large-scale foundation model for text representations. And then there's all sort of hybrid models at the interface of different data modalities, including text and images. That's another generative model from OpenAI that generates realistic videos from a textual prompt. So the main question that we were asking with our team at Microsoft about a year ago when we started this project is, could we also leverage these advances in foundation models to transform atmospheric forecasting? Because again, this is a setting that we think it was ready to be disrupted thanks to the very large volumes of Earth system data that are available, but also the diversity and the intricate question of all the questions, the research and the scientific questions that exist in this field. So this is where we came from, and that's our motivation. So we think atmospheric science is the first ripe ground for deploying foundation models in the sciences. And this is primarily because atmospheric science comes with literally exabytes of diverse and heterogeneous data. And just to give you a sense of scale, GPT-4 was trained on roughly 75 terabytes of data that basically capture most of the text we have access to in the internet. And now we're talking about petabytes and exabytes of data. So 1 or 2 orders of magnitude more data in atmospheric science and Earth system science that has not been tapped by any AI framework up to this date. This data could include real observations from satellites and other remote sensing tools like weather stations, buoys, balloons, ships, aircrafts, and they're collected around the clock. Like every second, there's data points that have been collected. And on top of that, there is actually physics-based models that have been developed over decades that allow us now to simulate weather and climate phenomena with some degree of accuracy. And this is really the tools that are currently being used in an operational setting to predict the weather. Like, you know, the forecast that you receive on your iPhone is some processed output of a weather forecasting model, which is formulated on first physical principles. So basically a system of PDEs that describes evolution of the atmosphere, subject to conservation of mass, energy, momentum, and so forth. And then supercomputers run in the background on a daily basis to produce those forecasts. Now, when it comes to atmospheric prediction, there is a class of different and diverse prediction tasks that one may be interested in. And here I'm sort of providing a taxonomy organized by the time scale of evolution. So on the left-hand side, you have a class of problems that are referred to as nowcasting, in which the goal is to produce very, very high resolution and accurate forecasts in very local regions in space and with high frequency in time. So nowcasting is the underlying physics is more or less deterministic, and it's governed by the evolution of atmospheric dynamics at short time scales. And basically, this is what we use to answer questions of, whether it's going to rain in London in the next 10 minutes. So basically, high resolution local predictions at local regions. Then on the right-hand side, you have a different time scale, which is roughly the 6 hour to 10 days or 15 days type of time scale. in which in order to resolve weather phenomena, you need to consider the evolution of those in a global scale because things are coupled over those time scales across the globe. So here we're looking at medium range global forecasting, which aims to produce meteorological variables at slightly coarser resolution compared to nowcasting. So nowcasting could be down to a kilometer scale. Medium range forecasting is currently done roughly at 9-kilometer scales or 10-kilometer scale globally. And again, the goal now is to make forecasts up to from a few hours up to 15 days. And then as you go further to the right, we go to longer time scales, seasonal and climate predictions. So basically predictions over a few weeks to a few months, all the way to full climate projections over the next couple of years or decades. And of course, this is just focusing on meteorological variables. There's a whole bunch of other associated tasks that are coupled to the evolution of weather variables. For instance, tracking air pollution, atmospheric composition, and atmospheric chemistry, in which case now you have to couple the transport of the meteorological quantities in the atmosphere with chemical processes and chemical reactions to keep track of concentrations of different species in time. So the two key messages here is this is a domain with vast amount of data and also a very large diversity in interesting scientific questions and prediction tasks that one can focus on. So the goal of a foundation model approach that we're pitching is to leverage this vast expanse of data. And hopefully we hypothesize that can allow us to build models that are more flexible in the sense that they can accommodate and they can process all this heterogeneity of data that is available there, because all these data come in different flavors, different resolutions, different number of variables. Some of them you can treat as images, some of them are just sparse measurements. So you need a type of model that can flexibly process this heterogeneous data. You want a model that's able to generalize, so exploit this concept of transfer learning to try to adapt to new scenarios and new prediction tasks in a data efficient manner. And also you want these models to be performant and potentially even improve in terms of accuracy in operational scenarios and in prediction of extreme events, which are probably the most important cases for which weather forecasting is important for our society. Today, I'm going to focus on two of those tasks, just to give you a highlight of a first foundation model that can actually do very well in two very distinct and different settings using the same model backbone for prediction. So we're going to focus on global medium range forecasting at different resolutions ranging from 10 to 30 kilometers globally. And also we're going to couple the atmospheric transfer problem with the atmospheric chemistry problem to also see whether this type of model can generalize to a new scenario, a totally new prediction task that involves new physics in terms of predicting air pollution and atmospheric composition. So I'll give you an overview of the model itself. I don't have a lot of details on the architecture, but I'm happy to take questions on that towards the end. So Aurora is a foundation model. And again, there's two steps of training it. And step number one is the pre-training phase, in which we're going to feed Aurora with many different data sets. I'm listing some of them that we used on the left, including reanalysis data from the ARA5 dataset, including climate simulation outputs from the CMIP family of data, and then also forecast data for weather from the IFS system, from the European Center for Medium Range Global Forecasting, and the GFS system from NOAA in the US. So all these data are going to be fed into Aurora. Aurora is going to be some type of large-scale vision transformer model. And in the pre-training phase, the prediction task is very simple. We're going to feed the model with some snapshots of the weather at time t and maybe at time t minus delta t, so two input snapshots. And the goal of the model is to predict the state of the weather at time t+1. What I mean, the state of the weather in this case, basically we're going to treat all those different meteorological variables like wind velocities and pressure and temperature and humidity and so forth. And each one of those will be a channel in a high resolution image. So basically we have the picture, the global picture of the Earth, and we have some special resolution of 9 kilometers globally. And then we'll have multiple channels corresponding to the target variables of interest. So Aurora is a type of encoder-decoder architecture. Its goal is to receive some inputs, and those inputs could have different number of variables and variable types and resolutions. It has a flexible encoder structure that will take these heterogeneous inputs and convert them into a unified representation in the latent space. Then in the middle of this architecture, there's going to be some transformer backbone that you could think of it as acting as a time integrator, basically. It's going to transform and advance this latent representation from time t to time t plus 1. And then finally, there's going to be a decoder module that will decode that latent representation back to the target variables that we want to predict. And of course, if you want to make predictions in longer horizons, you can evaluate this model in an autoregressive way. So this interval typically from t to t plus delta t will be a 6-hour or 12-hour interval, depending on the task that we want to solve. And then you can generate forecasts up to 10 days by autoregressively evaluating this model. So basically, you take the prediction, you feed it back as an input, and then you get the prediction t plus 2, t plus 3, and so on and so forth. So step number 1 is pre-training this model to learn this autoregressive mapping from all these diverse data sets. Once this is completed, there's a second phase, which is going to involve fine-tuning pieces of the model, potentially not all the model weights and all the model biases, but just the linear embedding layers of this model. We're using a technique called low-rank adaptation, and it's going to fine-tune this model to excel at different and distinct prediction tasks. So each prediction task will involve a different fine-tuning of the base Aurora model. So then we will have an Aurora version that is really good at high-resolution weather forecasting, or another Aurora version that is going to be good at predicting atmospheric chemistry. And the goal of the fine-tuning stage is to produce a model that can be operationally accurate and feasible. So you can receive operational initial conditions and then produce operational forecasts, hoping that those forecasts can compete with the state-of-the-art operational tools we have access to. So the goal of stage 2 is to really excel at various tasks, use a pre-trained model and fine-tune it for that. In terms of computational cost, the pre-training phase takes roughly 2 to 3 weeks on 32 A100 GPUs, so it's quite expensive. Fine-tuning stage is much cheaper. It takes roughly 5 days on 8 GPUs. So still some costs there, but not excessive. And again, in terms of the volume of data that goes to pre-training, we had a total collection of roughly 1.2 petabytes of diverse weather and climate data. We use a subset of that to train. Actually, we did a lot of ablation studies to understand the effect of different data sets and so forth. That's some of the results I'll show today. In terms of fine-tuning, we're fine-tuning on a specific data set for a specific prediction task that we want to get predictions for. So this is the outline of the results that I'll present today. And we have 3 different scenarios in terms of testing the model. I will start with the most surprising case, which is the ability of the model to predict atmospheric composition and atmospheric chemistry. And that will be done at resolution 0.4 degrees globally, which is roughly in the order of like 50 to 60 kilometer global resolution. Then we're going to talk about operational weather forecasting at high resolution, roughly 0.1 degrees globally, and that equates to roughly 9 kilometer spatial resolution. And then we're going to talk more a little bit about the ablation studies that sort of illustrate the merits of taking a foundational model approach to this framework, to this problem. So we'll talk about the scaling properties of the model and also the data ablation studies that I mentioned earlier. A few details about the pre-training before we go to the fine-tuning and the results in the different prediction tasks. This is the collection of data that the data pool from which we pulled and we created the training data set for Aurora. And what you see here is a combination of forecast data produced by physics-based models, but also analysis and reanalysis data, which is a blend of the predictions of a physics-based model and observational data. So analysis and reanalysis data basically involves a step of data assimilation that calibrates the output of a physics simulator to the real observations. The goal of using the hypothesis that we had and the goal of using all these different data sets is because there's a lot of variability in the way the atmosphere evolves. Each data set and each underlying model has its own biases and its own assumptions. So by exposing Aurora and all those different diverse data sources, we hope that it can actually expose itself to variability in different initial conditions, variability in different biases in all the models that were used to generate this data, and also in the inherent nature of the chaotic dynamics of the atmosphere. So by doing that, we hope basically that Aurora will learn to sort of average out all those effects and produce accurate forecasts. Now, as you see, each data set may have different spatial resolution. The data could correspond to a different period in time. Typically, we used training data, and I think this is a typo here. Our training data went up to 2021, not 2022. And we have different variables of interest. On the surface of the Earth, a bunch of variables like temperature, U, wind velocity, V component of wind velocity, mean sea level pressure, and then variables that are recorded at different levels in the atmosphere. So what we call pressure levels, again, include wind velocities, temperature, humidity, geopotential, and so forth. And then this is the number of atmospheric levels, so the different heights over the surface of the Earth at which we have recorded all these different quantities. And then finally, you see the number of frames. So this is number of T to T+1 paired frames for training that each data set comes with, and then the corresponding size in terabytes. So as you see, this is a fairly massive corpus of data, adding up to a total of 1.2 petabytes. The task of downloading and processing and building data loaders for this is just quite cumbersome. So like it requires a team of engineers that will work for a couple of months to do that. And I mentioned earlier the cost. So pre-training Aurora on this data took roughly 2.5 weeks. And I would say that this is sort of the models are still under-trained. We had to stop because we just don't have a lot of resources and a lot of time to complete. But if we keep training, things can improve. Now, the interesting task on predicting atmospheric chemistry. So this is a task that encompasses many of the challenges that in atmospheric prediction that Aurora aims to address. It's a task for which, unlike weather, it is data scarce. In atmospheric chemistry, we don't have data. If you go back to the pre-training weather data, you see that some of them dates back to 1979 or 1980. When we talk about atmospheric chemistry, there's only data for it maybe dating back to 2005-ish or so. And this data is actually changing a lot from one year to another. So the models that are used to generate chemistry forecasts typically undergo many updates. Their fidelity changes, their resolution changes. So there's a lot of data scarcity, data heterogeneity that we have to deal with. And that makes it really hard to just train a machine learning model from scratch to predict atmospheric chemistry. This is a setting that really we have to leverage this concept of a foundation model and transfer learning. The other interesting aspect is that now we have a model that is pre-trained only on weather data. So all those data sets that you see here correspond to meteorological variables like wind velocity and pressure. Whereas in atmospheric chemistry now, we have to generalize in a new domain, new physics, kinetic equations describing chemical reactions, and a new set of variables describing the concentrations of all those different chemical species. So now the main question from a scientific point of view is, could we actually leverage transfer learning, pre-train Aurora on weather data alone, and then try to fine-tune it on the scarce setting of atmospheric chemistry data to obtain forecasts of composition and air pollution? And if we do so, how accurate are those forecasts? And could we even envision that a system like that could compete with the state of the art in terms of operational systems like CAMS? So CAMS is like the standard operational system globally for making air pollution predictions. And I should mention here that atmospheric chemistry is also extremely expensive. So simulating weather with conventional tools typically takes a couple of hours on a large supercomputer. On top of that, adding a chemistry module makes those calculations roughly 10 times more expensive. So having a surrogate that returns predictions at a fraction of a computational cost is something that is quite impactful. So starting now from a pre-trained model, this is how we go about fine-tuning it and adapting the Aurora model to make these chemistry predictions. In order to adapt the model, we're going to use a smaller subset. So you remember earlier we had roughly 1.2 terabytes, but during fine-tuning, we have something in the order of 4 terabytes of data corresponding to CAMS reanalysis and CAMS analysis data. So this is atmospheric chemistry data generated by physics-based models at different resolutions, spanning different time spans. And now you see this addition of new variables that come into the model. In addition to the meteorological variables, now we have the concentration of different chemical species on the surface of the Earth and at different atmospheric levels. And then fine-tuning is again the same task, autoregressive prediction. The state of the system at time t comes in, including all the meteorology and the chemical variables, and the model predicts the state of the system at t+1. And the training, the fine-tuning here took roughly 1 week on 16 A100 GPUs. Now, once the training is complete, we're going to be evaluating our model on CAMS analysis data spanning a period of a couple of months in 2022. So as you see here, again, the data is fairly scarce. The highest fidelity data is the CAMS analysis data, and it only spans the period from 2017 to 2022. I'll speak a little bit more about the challenges about atmospheric chemistry data in this slide. Here you see an example snapshot showing nitrogen oxide map over the Earth. And like most other chemical variables in CAMS, it is very skewed towards high values in areas with large anthropogenic emissions and large anthropogenic activity. So you see all those spikes in India, in Asia, in some big metropolitan cities in the east coast of the US, a bit less in Europe. But in addition to the spikes, you have all this background signal corresponding to diurnal cycles because, you know, with the sun coming up and down, there's absorption of nitrogen oxide through different physical processes. So this is the type of data that we have to deal with. I mentioned earlier the data is scarce. We only have a few years worth of high quality data. The data is heavily non-stationary, so those distributions are non-Gaussian. You have a lot of skew towards this high concentration values in some peaks and then these background levels that you need to resolve. You also need to deal with distribution shifts because the source of the data is being updated on a yearly basis. So this CAMS simulator, every year there's a new version of it that generates new predictions, and those are affecting the way the machine learning models are behaving due to distribution shifts. Now there is spatial heterogeneity and all these diurnal cycles that need to be captured and resolved correctly. So these are some of the major challenges of, you know, why is it hard to build machine learning methods that work well in this setting? So this is a summary of the results now we have, and this is what I call a scorecard, and I'll try to explain what it is. So basically every pixel that you see here that has a color, red or blue, corresponds to the relative prediction error of Aurora versus CAMS for a given variable. So different panels correspond to different variables, including both meteorological quantities and also chemistry quantities. And then different levels of the atmosphere. So the bar plots on the bottom are on the surface of the Earth, and the plots that you see the panel on the top correspond, different rows of each panel corresponds to a different pressure level above the different height on the atmosphere, basically. And then the x-axis is the forecast days. So we're making forecasts for 5 days into the future. This is a model that was fine-tuned to make 12-hour forecasts. So we do 2 steps of forecasts for each day. And basically blue here means that Aurora produces a more accurate forecast than CAMS. Red here means that Aurora produces a less accurate forecast than CAMS, which is the state-of-the-art operational system. So what do we see here is first of all, we see that Aurora is more or less competitive with CAMS, meaning that it is within 20% in RMSE in 95% of all targets. So all variables across all lead times up to 5 days, all pressure levels. It matches or outperforms CAMS on roughly 74%. So 74% of that picture is blue instead of red. And we see that we're lacking performance in 2 key quantities. We're lacking performance in some of the surface variables, like the particular matter variables that basically describe the transport of finite size particles of different size on the surface of the Earth. And one of the reasons here why Aurora doesn't do so well is because it was not provided with any emission data as inputs. So a lot of those variables heavily depend on pollution and anthropogenic effects. And Aurora did not have any of those as inputs. Instead, it sort of implicitly tried to infer them from the historical CAMS data that we gave it access to during training. So we believe that if we were to improve that part, we would see an improvement in how well we can predict those pollution variables. Another variable that Aurora struggles with is the ozone on the higher levels of the atmosphere. And again, this is it has to do with the quality of the measurements we can collect there and how well the training data has been calibrated over there. And finally, another piece is that at very short lead times, 12 hours to 1 day, CAMS is more accurate than Aurora, but in longer predictions up to 5 days, we get better RMSE performance. Now, the main message here is that this is a system that seems to be competitive, more or less. This is the first time an AI method sort of was developed in this setting, and it seems to be competitive with the state-of-the-art operational system. However, predictions now can be obtained in roughly 6 seconds on a single GPU instead of spending a day on a supercomputer. And this is just another plot just to show, again, the relative performance. So CAMS is the baseline, normalized at that horizontal line at 0%. And this is the relative root mean squared error of Aurora versus CAMS. Anything below that line indicates better performance. Anything above that line indicates worse performance. And just as an indication that the model is not predicting something trivial, we're also plotting what we call the persistence prediction. So persistence means that, okay, we assume that the way the weather or those chemical quantities do not change from one day to the other. So we assume sort of like a constant, which indicates that indeed there's dynamics to be resolved here, and the persistence is a very inaccurate estimator. And the take-home message is that at the 3-day mark, Aurora is competitive with CAMS on all variables and matches or outperforms CAMS on roughly 86% of all variables of interest here. Any questions? All right, maybe we can save them for the end. Moving on to the next task, which is producing 10-day global weather forecasting at high resolution of 0.1 degrees globally. The current gold standard for operational weather forecasting is set by the IFS HRES system operated by the European Center of Weather Forecasting. And it's a numerical weather prediction system that runs at this resolution. Building accurate models using AI methods in this setting is also extremely challenging. There's a lot of work that has been done in building AI models for weather forecasting, but up until this day, all of them operated at much lower resolution. So the GraphCast system by Google DeepMind operated on 0.25 degrees, so roughly 30 kilometers globally. Same thing with ForecastNet by NVIDIA or Pangu Weather. They were all limited to 0.5 degree resolution. This is one of the first attempts to actually scale to 0.1 degree resolution. And again, it's very challenging from an engineering infrastructure standpoint. First of all, there's a data scarcity issue because we were not able to generate high resolution weather forecasts until 2016 or 2015. That was the first time we had access to a simulator that could predict at this resolution. So unlike the reanalysis data that go back to the 1970s, high resolution weather data is sort of still scarce. And also the data complexity itself, just a single data point, just a single snapshot of the weather at 0.1 degrees, including all the variables, is basically an image that has a resolution 2000 by 4000 by roughly 200 channels, and is more or less close to 2 gigabytes in size. So that's just a single input to the model. So you can imagine that this can present a stress test for all components of a machine learning pipeline. So all this data lives on the cloud. You need to download them. You need to build data loaders. You need to fit things to GPU memory. So it's a kind of intense task to get it to work and get it to perform well. So again, now the question becomes, can we take Aurora that was pre-trained on lower resolution data, because all the data that I showed you earlier had higher resolution, the highest resolution was 1/4 degree, so roughly 30 kilometers globally. Can we take that model and fine tune it to much higher resolution to unlock this new capability? And the way we'll do it, we'll take the pre-trained model and fine tune it on this IFS HRES data, spanning the time from 2016, and I believe it's still 2021, not 2022. And fine tuning again takes 1 week on 16 GPUs. And then finally, we're going to evaluate on the year 2023 to test the performance. And again, you can contrast the size of the fine-tuning data, which is roughly 20 terabytes versus almost a petabyte that we use for pre-training. And now this is a scorecard comparing Aurora to the state-of-the-art operational weather forecasting system, which is IFS HRES at 0.1 degree. And you see a quite strong picture here. Again, blue means better, red means worse. And basically, Aurora is just worse, again, at very short lead times of roughly 6 to 12 hours. And at levels of the atmosphere, a little bit higher up in the atmosphere. You see there the geopotential variable Z is a bit worse higher up in the atmosphere. But the take-home message is that Aurora outperforms the state-of-the-art operational system on over 92% of the targets. Performance gains are most pronounced at longer lead times with consistent performance. And now again, we have a system that can predict the next weather state in roughly 1 second instead of hours on a supercomputer. Yeah. What's 6 hours? It has to do with the fact that we're starting from, so the operational system is very well calibrated. So in its initial condition is very well calibrated to the analysis data that is used for evaluation. So it's very hard to beat at this very short lead time. It basically contains all the right structure and biases that the machine learning model is missing. In addition to comparing against simulation outputs, we also try to compare Aurora versus the IFS system against weather measurements. So this is against observational data collected globally at different weather stations at different locations. And again, what you see here is two different error metrics, root mean square at the top and mean absolute error at the bottom, averaged over the entire test year, 2023. And we see again that for different lead times, IFS is still competitive at short lead times, but as we go up to 10 days, we have a clear improvement in performance for Aurora. And here what we're plotting is the temperature at the surface of the Earth, but similar trends can be observed for other variables of interest and at different atmospheric levels. Now, this is an interesting case study. So a lot of work has been done the last few years, and a lot of different models have been proposed in terms of AI models for weather forecasting. And one of the key questions we always get is, okay, those models can do a decent job at predicting typical weather. How well do they do at predicting extremes? And that's still, I wouldn't claim that AI models can do exceptionally well at predicting extremes, but this is a really nice case study to illustrate some of the pitfalls and the drawbacks of AI models. So Storm Ciarán was a storm that hit the western coasts of Europe. So basically the UK, Ireland, the Netherlands were heavily impacted from the storm, and it took place in late October, beginning of November of 2023. From a meteorological standpoint, it's considered to be a rare event. It's basically the lowest low pressure ever recorded in November in the UK historically. So it was sort of like a surprising event the way it evolved from a meteorological standpoint. And recently there was a Nature paper by Charlton Perez that basically took all the existing AI tools for weather forecasting. It tried to benchmark them for this specific event, but also some rare events in general. And the take-home message of that paper is that all AI models, they can do fairly well in predicting typical weather, but they were not really good at capturing the spike in maximum wind speed that occurred during this event. Interestingly, we tried to run some ablations, and the high-resolution version of Aurora, the 0.1 degree model that we trained, it seems to do quite well. You see on that panel, you see on the left-hand side, the maximum wind speed on different timestamps from October 31st to November 2nd. And you see there the IFS model, which is sort of considered to be the ground truth, is this black line on the top that correctly captures the intense onset, the intensification of the storm. Whereas all the existing AI models up to this point, including GraphCast and Pangu and ForecastNet, basically really underestimated the maximum wind speed by quite a lot. And it was interesting to see and sort of surprising to some extent that Aurora was able to kind of close that gap and get a better estimation of the maximum wind speed. And in fact, here I'm showing the result for the 0.1 degree Aurora model, but we also, one might say, okay, hey, you just have a higher resolution model, therefore you can resolve those convective effects more accurately and you get a better answer. But even the quarter degree resolution Aurora version that is sort of operates at similar resolution at GraphCast and Pangu still gives a very similar result that is improved. This is just an indication, it's not a conclusion that Aurora excels at extreme events. We have more thorough studies in the paper that indeed we show improved performance at extreme events, but it's not the end of the story. So there's still more work needs to be done to make sure that those AI models are more robust at estimating extremes. All right. Entering the last part of the talk, in which I'd like to talk a little bit about the machine learning aspect of this, not in terms of architecture, I'll save it for the end, but more in terms of the foundation model concept and this whole point of using diverse data for training, going beyond the single data set and also increasing the model size and test the scalability of the model. So here I'm going to show you how the performance of the model is changing as a function of different data sets that were used for pre-training. So we're going to start from a baseline. We're going to take the Aurora model, train it only on the ERA 5 dataset, which up until now was a standard way of building machine learning models. So GraphCast, Pangu, all those models were only trained on ERA 5. So what you see here is validation performance. So it's normalized RMSE for a model So, okay, so the baseline is the model that is pre-trained on ERA 5 alone. That's why all those curves are normalized to 100. And I'm going to start comparing now models that are trained with a different mix of diverse data sets. Step number one is we're going to go to case 2, and we're going to compare a model that was trained on ERA 5 alone versus a model that was trained on ERA 5 with the addition of some low fidelity climate data. Which is surprising, right? ERA 5 is a high fidelity weather data set. Now we're adding to that some low fidelity, low resolution climate data. You shouldn't expect to see a massive improvement, but indeed there is some improvement. So on the left-hand side, we have a bunch of surface variables. On the right-hand side, we have the performance, the average performance over all variables for different atmospheric levels, okay? And what you see here is that indeed by adding some low fidelity data from the CMIP family of datasets improves the generalization performance. It's a little bit surprising, but that was a result that we obtained. Now, going beyond that, that gave us a first indication that the data plays a role. And even though you want to predict, so the validation set here is ERA 5 still. And it's still a bit surprising that you train a model in ERA 5, you want to predict at ERA 5, but now if you add some additional low fidelity data, you get better performance at ERA 5. So that was one of the first indications for us to start exploring this data dimension axis of adding more and more diverse data. So in a different case study, we took the case 2 setup, and we augmented that with more data. We used the ensemble forecast data from the IFS system, the ensemble mean, and then the HRES forecasts. And what you see here is the same now performance against a model that is normalized for ERA 5 alone. And again, we see quite some improvement across the board, except for some of the atmospheric levels that the improvement is not so large, especially higher up in the atmosphere, atmospheric level 50, we actually have worse performance. But the take-home message is that adding even more simulation data seems to improve performance on most surface variables and for the atmospheric data that was present in this newly added data. So when we added the IFS ensemble data, the range of atmospheric levels for which we did have access to ensemble data was in the range between 500 and 1,000. And you see that the performance gains there are consistent, whereas in the atmospheric levels for which we didn't have IFS ensemble data, the conclusions were not entirely clear. Taking a step further, case 4, we augment now this with even more diverse data from the GFS system, which is the American prediction system, basically from NOAA. C4 is the model that achieves the best overall performance. So it's the same model architecture. We didn't scale the model itself at all. This is just playing around with the diversity of the training data corpus. And then also trying to keep roughly the total size of training data fixed to sort of have a quote unquote more fair comparison, although this is hard to control. So C4 achieves the best performance overall with the improvements across the board, leveraging good coverage of all pressure levels, in addition to using analysis data from the GFS system. So this is basically, the C4 was the kind of flagship model that we pre-trained. And this is the pre-trained model that generated the results I showed you earlier after fine-tuning. Now, another aspect that you may expect is that by adding more data and more diverse data, we should expect to have better coverage of extremes. And indeed, this is the case. This is here we're comparing, again, the similar ablation, case 1 to case 4, but instead of measuring root mean squared error, we're measuring thresholded versions of RMSE in the tails of the data distribution. So where more extreme values, either extreme lows or extreme highs exist. So on the left side of those panels, you see performance at extremely low values, and on the right-hand side at extremely high values. Everything is against normalized versus a baseline, which is case 1 for the ERA 5 dataset. And this is showing a 6-hour lead time root mean squared error relative error. And basically everything that is below that blue line indicates better performance. And the take-home message is that pre-training on diverse data improves forecasting of extreme values across all variables. And interestingly, the results also hold for derivative variables that were not used for training. So for instance, wind speed is a nonlinear combination of the U and the V components of wind velocity, and still we get improved performance for the extreme values of wind speed when more diverse data is used. And we think this is one of the key enablers, going back to that Storm Ciarán case study where Aurora did very well in predicting the maximum wind speed for this extreme case. We hypothesize that this improved performance comes from the diversity of the data that was used for training. Finally, I'd like to make a comment on the model's scale. Aurora is a transformer model. We know that transformer models in deep learning benefit, and kind of predictably their performance improves with increased scale. By scale, mean the size of the model. So to sort of try to probe this, we trained 3 different versions of Aurora. The first one with 113 million parameters, and a medium size with 660 million parameters, and then the actual model that we use for all the prediction tasks, the most accurate model, which is 1.3 billion parameter model. Take-home message is bigger models obtain lower validation loss for the same amount of GPU hours, meaning that there is a bias here to use bigger models. So you can actually achieve better performance if you have a finite number of compute resources and training time. You can achieve better performance quicker by using a larger model. We fit a power law, just, this is a rudimentary version of a scaling law with only 3 data points. So, okay, that's a little bit silly, but that sort of indicates a slope of roughly negative 0.073. Take-home message is that if you roughly double the model size, you get a 5% improvement in performance in a sort of predictable fashion. And then finally, we had to compare against what's out there in terms of state-of-the-art AI models, not just the operational systems. For many, what the state-of-the-art is considered to be the GraphCast model by Google DeepMind. That was a graph neural network that was trained on the ERA5 dataset, and then it's evaluated operationally against the IFS system at 1/4 degree global resolution, which again, roughly 28 to 30 kilometers globally. And this is the same type of scorecard that I showed you earlier. Every pixel basically measures the relative mean squared error for different variables at the surface or the atmosphere, and for different lead times of up to 10 days. So the x-axis is 10 days forecast. Take-home message is Aurora outperforms GraphCast on roughly 94% of the targets. Biggest gains are observed in the upper atmosphere, for which the performance of GraphCast is known to be poor. There's larger improvements up to 10 to 15% observed at short and long lead times. The smallest improvements, or the cases where GraphCast was better, was for the specific humidity variable closer to the surface of the Earth in the 2 to 3 day window. But that was really the window for which GraphCast was sort of heavily optimized. So the fine-tuning of GraphCast was performed for sort of this time window. So it's not a surprise that it's still a very strong model there. But the take-home message is that, and again, now the comparison is at the same resolution. So we fine-tuned the version of Aurora at 1/4 degree instead of 0.1 degree, just to make this comparison. All right, so this is it. I can save some time for discussion. So summary is that foundation models are setting a new standard in machine learning for environmental prediction. I think that was sort of like a first step to demonstrate that at a realistic operational setting. Aurora is the first large-scale foundation model in this domain, and it shows improved accuracy, resolution, and adaptability across a range of operational prediction tasks. There's a lot of next steps that certainly our team cannot carry out on their own, but hopefully that will spark some interest, and domain experts and others can contribute and pick up some of those. The first immediate one is that Aurora is a deterministic model currently, but for weather prediction, you need to have probabilistic outputs. The atmosphere is a chaotic system. You can only predict it up to like 7 to 10 days. If you want to go beyond that, you can only make probabilistic predictions. But it's relatively straightforward in terms of taking a deterministic model like Aurora and extending it. You can have either an ensemble of Aurora models or attach a diffusion prediction head to it to generate probabilistic forecasts. Another really exciting and important area is to go towards the nowcasting regime and tap into local high-resolution data, regional data over specific areas in the world. There is a wealth of data over the US and over Europe, less so for Africa and other sort of more developing regions. But again, these concepts of transfer learning are super interesting here. Can we fine-tune a model with high quality, high resolution data over the US? And can we expect it to then generalize somehow or be fine-tuned to make accurate predictions over Africa, where we have a scarcity of high quality data, or the polar regions, for instance? Up until now, Aurora was trained only using simulation data, so model output data from simulations and physics-based solvers. Extending to also incorporate observational data directly is an interesting direction. So far, observational data only came in indirectly, implicitly, because some of the reanalysis data from the simulators are calibrated to observations, but we did not use observational data from satellites and other sources directly here. And then expand the capabilities to other prediction tasks like seasonal prediction, climate projections. And then ultimately, given the flexibility of all those systems, it kind of suggests an alternative way to start modeling and coupling different subsystems of the Earth. So potentially in a future version, you could think of coupling an atmospheric prediction module with an ocean prediction module and so forth. But of course, that will take years to get there. There's a preprint online. There's a few blog posts and articles that have been written if you want a more layman terms introduction to what we did. I'll just conclude with just introducing the rest of the team and acknowledging their work. It was not a large team, surprisingly. Most of the work was done by the 4 people that you see on the left column, minus me. I didn't do much technical work. I was mostly supervising. And then we had some external sort of consultants and collaborators and help on the engineering front. So yeah, that's all. Thank you for your attention. Happy to take questions. Yeah.
So thanks for the great talk, Ari. I mean, I have a lot of projections, some of which we already discussed, but I wanted to ask a more like general question, right? So, for example, do you think that it's the architecture that matters more or the data that you use? Like, for example, when we compare foundation models nowadays, in some cases we don't even know the data set that has been trained on. And when comparing to graph has, one would say, well, a graph doesn't include the aspect of geometry, let's say, so it's modeling, let's say, the inductive bias of the data in a way, yet it underperforms here. So could it be that it's a matter of, let's say, the data in a specific regime, or
Yeah. So the question was, what is more important? Is it the model design itself or the data that we're training on? I think I'm fairly confident to say it is mostly the data, and having high quality data and diverse enough data that sort of, covers the relevant data distribution is probably more important in this domain in which you have access to tons of data. Is probably more important than the inductive biases you built in the model. But of course, I should also say that in order to process this data, which is very heterogeneous, different resolutions and so forth, you need a model architecture that is flexible enough to accommodate that. And one sort of drawback that we sort of recognize in GraphCast is that it's really hard to be adapted to handle inputs with different resolutions and so forth. It requires a lot of engineering. Whereas here we opted for an extremely simple model from an ML standpoint. I can talk more about the architecture details if you're interested. It's basically a Swin vision transformer at its backbone. And all the innovation comes into the encoding aspect of, how can you process inputs with different resolutions and so forth. But the model design choices we made were intentionally simple to enable this aspect of accommodating diverse data. And that seemed to be kind of like the winning factor here.
And maybe a small follow-up. Does the model handle well cases where you have mixed data? So let's say you have this 3D latent tensor. In order to construct this tensor to fit into the model, do you need to have all that data sources available, or something missing and then you, let's say, interpolate or?
So you could have missing data in the sense that the model can accept varying types of variables. So in one data set, you might have some variables, in another one, maybe not. During pre-training, you can also sort of mask the tokens and intentionally sort of, have a masked auto-encoding type of objective. So to some extent, it's robust with respect to missing data. Yeah.
Yes, thank you for the talk. I want to ask, do you take into consideration that maybe each data set has a different fidelity?
Yeah, so indeed, to some extent, yes, in the sense that, we have this loss function that averages over everything, and we do assign weights to place more emphasis on what we consider higher fidelity data versus the other. So ERA5 had a higher weight versus, let's say, the ensemble mean data, for which we know that the ensemble mean is sort of like a much smoother forecast that averages over multiple trajectories. So yeah, during the training, we had some weighting scheme that was manually adjusted to account for that.
And a follow-up question about the number of, you just give one time step as input, right?
2 time steps.
2 time steps.
Yeah.
Okay. Okay, thank you.
Any other questions?
And we may have questions online. But maybe I can ask a question. We discussed this before during our one-to-one discussion, but it's interesting, I think, to maybe repeat your position. So Aurora is not a physics-informed machine learning model. It doesn't know any underlying physics, and still we're talking about a system that is, pretty much completely governed by physics. So how do you explain that it performs so well, even though it's not physics-informed?
Yeah. I think the short answer to this is that the physics is in the data here. All the data sets that were used to pre-train Aurora are outputs of physics-based models. And I would even argue, and these are different physics-based models. So I would even argue that, and that's one of the main motivations of why we took this approach, is that potentially every one of those physics-based model outputs opens a new window to Aurora to kind of maybe learn something about atmospheric dynamics. Different data sets contain different variables, different resolutions. Some data sets, for instance, resolve atmospheric dynamics really well in the z-axis, like the MERA2 data set. Others resolve everything in the XY axis better. Some of them contain, different variables, as I said. So the kind of hand-wavy answer to this is that all those different data sets have something to say about the underlying physics. They're generated by physics-based model. So the physics is there in some sense. And Aurora learns from that data by the whole concept of taking all this data and compressing it into the weights of a neural net and then making predictions. We hypothesize that it has to learn something about atmospheric dynamics. It's hard to assess that and quantify. Of course, you can always post-process and say, hey, does this output conserve mass or momentum? There's been already some studies, or not for Aurora, but for other AI models. And the answer is that yes, more or less it does, not perfectly accurate, but it seems to be physically consistent. So yeah, overall, my take is that in regimes where you have access to tons of data, like petabytes and exabytes here, it's probably not so important to worry too much about inductive biases and model design and physics constraints. Just, let the data speak and learn from it. In regimes where you don't have access to all that data, then you should be using all that additional structure and priors and inductive bias as a mechanism for compensating for the lack of data.
Are there anyone who can talk from online? Any questions? No?
There's one question back.
So I would like to make a question. Maybe it's a bit naive, but as far as I understand, the idea here is use as much data as you possibly can, and everything will come up. Like let's say the dependencies will find their own way to reveal themselves. So I was just wondering if doing this fine tuning in the second phase of what you presented before is kind of counterintuitive, because introduce some biasness into the model, or is it just?
Yeah, I mean, at the end, you always have a prediction task that you want to tackle. And the fine tuning stage was really taking a model that is more of a generalist model and making it focus at a single prediction task. So for that phase, you want to provide high quality, high fidelity data for that specific task for the model to be fine tuned on. That's where sort of like the performance comes from.
Thank you.
Yeah, I see something in the chat. Yeah. Do you publishing the weights? Yeah, so we will be publishing the weights. So currently we have a preprint online that we're working on and polishing a few things. We got feedback from experts. We plan to submit the paper for peer review probably within the next week or so. One of the requirements of the journal is that we should make the model open source, at least the model weights and the evaluation part. So that's something we're working on. And I think by the end of the summer or so, we should have like a lightweight library that allows users to just download the weights and feed some inputs, get some predictions. Publishing now the entire pipeline is going to be more difficult. On one hand, we have to go through all the internal Microsoft approval, which is a little bit of a nightmare. On the other hand, I don't know how useful that would be because it's like a big code base, not a lot of documentation. It's not going to be easy for someone to just pick it up and make it useful. Of course, given the fact that you need to store a petabyte of data somewhere and train on many GPUs, that infrastructure part makes it complicated to open source everything and share it more broadly. But yeah, we will be publishing the weights and the evaluation of the model. That is for sure. Maybe with some examples on how you can fine tune the model and so forth. But the pre-training pipeline it's heavier and probably not very useful. Yep.
Thank you for the talk. You gave a list of things that can be done next, but I would like to see what exactly are your plans for this? So what are you going to do next with this? So Aurora is going to be published now. You showed some, let's say, capability, but what's the sort of longer term plan for this research?
Okay, so really the short-term plan is to go through peer review, get experts to evaluate more thoroughly and so forth. We are having ongoing discussions with some of the major weather forecasting organizations, including NOAA and the Met Office in the UK. They have specific problems they're interested in and use case scenarios, and we're going to be working with them to extend Aurora to accommodate that. I think one area of particular interest, which seems to be a relatively low-hanging fruit, is this extension to regional and high-resolution data. So that's probably one of the more kind of near-term enhancements. There's some also opportunities on the climate side of things, but things are a little bit more difficult. Data is scarce. It's hard to validate and evaluate things. There are some ideas there, but yeah, maybe I know that part of my team is already working on seasonal prediction. So yeah, I would say the last bullet, seasonal prediction, climate projection, is one area that one can start looking into given what we have. And the other one is the local nowcasting. What I would be super excited to see, but I don't have the bandwidth to do, is to kind of expand this along the physics axis, like atmospheric chemistry, or have a system that also couples things to the ocean or other subsystems. But that's a bigger vision, longer term project. It's not so easy. And also observational data, like having an end-to-end system because all we have now is a surrogate for the forecasting system. We're not touching the data assimilation part. So we still need the traditional pipelines to provide an initial condition for us to do the forecast. But I think the holy grail would be to have an end-to-end system that can take raw observational data, produce those initial conditions, do the forecasting, and then predict back at specific locations. I think, yeah, within the next few years, we'll see something like that.
Okay, thank you. Very inspirational. But at the end of the day, it remains an empirical model, right? So now you're talking about climate projections, but we see things, I mean, greenhouse gases, permafrost melting, which hasn't been observed before. So is this really something that you say, well, we have a lot of, hope that we can do climate projections with this kind of models?
Yeah, so the more realistic hope is that we can build a surrogate to a very expensive climate simulator, and which we could trust to the degree that we trust a climate simulator. That's probably the most realistic thing we can hope for at this point.
Any other questions? If not, let's thanks Professor Perdicaris for this presentation. We can continue outside with slides and
Percival?